Welcome back to 8701. So this is our last video in the chapter on neutrino physics, and we'll talk about mass scales and the nature of the neutrino particle. Very briefly, when we think about how we can measure the neutrino masses, there is a number of methods which come to mind. The first one is to just look out into the universe and try to understand how much matter in total could come from as a source from neutrinos. And one has to make assumptions about the model, the cosmological models at hand. But if one accepts those potential biases or model dependencies, one finds that there's a potential reach of this kind of mass measurements of 20 to 50 MeV, milli-electron volts, and the current best limits are in the order of 0.1 to 1 electron volt. A second source, and I'll talk more about this later, is the study of neutrino-less beta decay, double beta decays. Here, the current best limits are in the order of 0.2 to 0.4 electron volts, and there's a chance to reach 20 to 50 milli-electron volts. This kind of measurement will also answer the question whether or not the neutrino is a Dirac particle or a Majorana particle, as we discussed in earlier lectures. And then there is the more classical approach of measuring the mass of a neutrino from the endpoint spectrum of beta decays. And so here, the current best limit is from the Katrin experiment, and I'll talk about this on the next slide. And it's in the order of 1 electron volt, and there's a potential reach to go down to 40 milli-electron volt. So currently, the range is in the order of, the range of limits is in the order of 1 electron volts or a bit better, and one will be able to go down to limits in the order of 20 to 50 milli-electron volts. So here is a cartoon of how those measurements are being conducted. One starts with tritium and uses beta decay. And this lecture overall is a good kind of first entry into the nuclear physics program, where we discuss beta decays and other nuclear decays in more detail. What we find here is that we find an electron and then neutrino, antineutrino in this case, being emitted. And so the name of the game is now to measure the electron energy as precisely as possible, and then find a sensitivity of the neutrino mass in the endpoint spectrum. And those small differences here in the endpoint spectrum, they then lead to understanding of the mass of the neutrino, because the total energy in the collision needs to be preserved. And so the entire story here is about how precisely can we measure the energy of the electron in order to infer the neutrino mass in that. And so the latest results came out last year from the Katrin experiment, and shows that we can set an upper limit. The result is consistent with a neutrino mass of 0, and that we can set an upper limit at 90% confidence level that the neutrino, electron neutrino, is of mass of 1.1 electron volt. Just as a reminder, we measure the mass of the electron neutrino in this decay, which is the sum of the individual components, mass eigenstate, which make up the electron neutrino. To set the historical context in this discussion here, we find that this latest result is an improvement of the order of factor of 2 compared to previous result by other experiments, which had the very similar job to measure the electron energy in beta decays, in the endpoint spectrum of beta decays. There's a new approach which has been proposed by Joe Formaggio here from MIT, which changes the way the electron energy is being measured. So the idea is to have the decay happen in magnetic fields and use the cyclotron radiation of single electrons. So the advantage here is that one doesn't have to move the electron somehow into a spectrometer, but can immediately measure the energy of the electron And the measurement of the energy then turns into a measurement of the frequency, and basically measures the cyclotron frequency of the electron circling around in a magnetic field. And so it turns out that one moves the measurement of the energy of the electron into a measurement of a frequency. And those frequency can be measured with very, very high precision. So there's some hope that this kind of measurements lead to very, very precise results of the energy of the electron, and with that the mass of the neutrino. So the last slide here is now, how can we figure out whether or not the neutrino has Dirac or Majorana nature? And this can be done, or the highest sensitivity comes from so-called neutrinoless double beta decays. So one starts with nuclear decays where 2 electrons are emitted, but no neutrino. And so this requires that in this process, there's a transition which includes the neutrino, where the neutrino has to be its own antiparticle. And that just means that the neutrino is of Majorana nature. This is being done by measuring, again, the energy spectrum. You typically have all kinds of background contributions, but also backgrounds from double beta decays with 2 neutrinos. So you see the spectrum here. And then you look at the endpoint of this part here and find that there is this peak, a very precise, sharp peak of energies, of the 2 electrons. The issue is that forecasting where this peak is requires a proper knowledge of the dynamics inside the nuclei here. And those measurements are being conducted. There's many of them conducted in various nuclear transitions or decays, and they haven't yielded a positive result yet. Research is still going on this end.